Okay, good afternoon, everyone. Today we're very pleased to have Professor Eduardo Prosichetti visiting us. Eduardo is an assistant professor at Florida Atlantic University. His research interests include public key cryptography and number theory. And in particular, his research focuses on code-based cryptography, and he is involved in four submissions to the NIST post-quantum cryptography standardization process. And today, Eduardo will tell us about reproducible codes and its cryptographic applications.
Thank you, Hao, and thank you, Christine, for the invitation. I'm very happy to be here. Now 3 submissions, not 4 anymore, but okay, still going. So yes, this is one of the things I've been working on lately with my colleagues Paolo Santini and Marco Baldi from Università Politecnica delle Marche in Italy. So here is an overview of the talk, and I apologize to those of you that are very familiar with coding theory. Hopefully not too many of you. For sure, Christine, some things are going to be obvious. But I'm going to have to do a little bit of preliminaries and then talk about sparse matrix codes, or what we call sparse metric codes, and then introduce the concept of reproducibility, and then talk about codes in reproducible form, and a little bit of why we're doing this, how we defeat possible attacks, and some explicit constructions. So the motivation, in fact, for most of my work, I want to say, is that, as you are well aware, we're very scared of large-scale quantum computers. Small-scale quantum computers are available already, Microsoft included, I guess. But once this reach a desirable size and stability, then things like Shor's algorithm are going to kill off all of the public key crypto that we're using so far. And so then we started this process with NIST, the National Institute of Standards and Technology, 2 years ago, almost now, I think, for standardization, so that we can update the current standards for encryption, digital signatures, key exchange. And right now we have about 5 areas that are involved in this. Code-based cryptography is one of them. This is what I'm working on. But also lattice-based, hash-based, multivariate cryptography, and isogen-based cryptography are other valuable candidates with regards to this. And so what is the input for this work is that most of code-based cryptography traditionally had to deal. So code-based cryptography is a very old area, started in '78 with Robert McEliece, about the same time as RSA. But it was always kind of overlooked in favor of other things, mostly because of its very large public key. And so a lot of research lately has been focusing on reducing the public key size. And for this, we use structured codes that have some sort of algebraic structure to help reduce the public key size. And in fact, we get candidates that are very appealing. However, you have to be very careful with this, because introducing additional structure to codes that are already structured may compromise security. And there's a long history of unsuccessful proposals in this sense. But what we call generally sparse metric codes, LDPC codes have been around for many, many years in communications. So that stands for low density parity check. More recently, moderate density parity check have made an appearance with cryptographic relevance. And these are just codes that are defined by the fact that they admit a parity check matrix which is very sparse or relatively sparse, but they don't have any other constraints, and so they are less affected by additional structure. So it seems like this is a promising idea. But, so far all the work with LDPC and MDPC has been using QC, quasi-circular and quasi-cyclic codes. This is very simple variation where the code is, in fact, quasi-cyclic, so it's invariant under a certain amount of permutation cyclic shifts. But can we do it differently? Can we maybe generalize this? Because the suspicion that we had is that maybe people have not looked into this enough. And in fact, we have a pretty strong hint. Now, 2 summers ago, I visited Adi Shamir and we had a pretty enjoyable conversation. And he said, like, but why do you guys always use QC? You know, just why don't you do something different, right? And then and so this is how this work started. And we said, yes, this is probably a good idea. So maybe we can just expand the array of tools that we can use in this sense. Okay, so quick preliminaries, maybe not too much, but just to recap what we're talking about, error correcting codes. So linear codes are just subspaces, vector subspaces of certain dimension of fq to the n. And normally we're interested in codes that have a certain decoding algorithm associated with it, so they correct up to a certain threshold of errors. Yes? We measure these things, at least for traditional code-based cryptography, with Hamming weight, or traditional code in theory, I should say. So it's just the number of non-zero entries. And we define codes by means, well, one of two ways. We can define them with a generator matrix, which means that we basically choose a basis for the subspace, and then we put it as rows of the matrix, and then we can generate code words by just doing m times g. We can also put this in systematic form. This is one particular choice of generator matrix. Of course, as you can imagine, there is more than one, because there's more than one choice of basis for the subspace. The other way that we can define codes traditionally is with the parity check matrix, which defines the code as a null space, so the kernel of this matrix H. So a code word is in the code if it has what we call syndrome equal to 0. And again, there is a systematic form for this, which is related to the systematic form of the generator matrix, and this is because, this one, in fact, is generator matrix for what we call the dual code, and so they are strongly related to each other. Yes? Okay, so how do we use this in cryptography? As I said, in 1978, this incredible contribution by Robert McEliece, very short technical report from Bell Labs, 4 pages, if I'm not wrong, in which he introduced this cryptosystem based on linear codes. And the point is that what's the hard problem underneath it all is that it's hard to decode random linear codes. So if we just have a generic code given by, say, a random generator matrix, then we cannot use any decoding algorithm that is associated to it. And so we can only use generic techniques to try and decode. Now the point, of course, is that we want to do this public key, so this will become our trapdoor. Yes, so we want to have a code that is decodable, but we mask it so that it looks random, essentially. So the key generation chooses a code family. Traditionally, McEliece did this with binary GOPA codes, and we're still not sure why. And now we can't even ask him anymore, because some of you may know he passed away recently. But this seemed to work quite well for all these years. But it could be, in principle, any error-correcting code family. For example, a DPC or other families, yes? And then we create a generator matrix. We sample a generator matrix. We scramble it. For example, McEliece suggests to do SGP, where S is an invertible matrix. So I'm just, again, changing the basis, right? And then P is a permutation matrix. So I'm swapping columns around. I get what is called an equivalent code. And so I'm definitely far away from the original code now. And this should look random. This is not the only way, and we will come back to this. But in principle, this is the simplest thing you can do. Yes, transformation on the left and the right. And then we just encrypt our plaintext as a noisy code word. Yeah, so we take our plaintext, we put it in a code word, and then we sample some randomness. So the cryptosystem is probabilistic, yes, and we flip some bits essentially. And then the decryption uses the private key, which is mostly the input to the decoding algorithm, right? So, okay, we may have to get rid of SMP at some point during the decryption, but basically the point is that because I know the private description of the code, I have access to, for example, the GOPA decoding algorithm, yeah, Patterson's algorithm, or equivalent choice of decoding algorithm if I'm using a different class of codes. So the description is extremely simple. As I said, it was 4 pages. And in particular, what you can observe is that encryption is very fast, in particular encryption, because it's really just vector matrix multiplication and then add some errors, which means really flip some bits. Decryption is a little bit slower because it involves a decoding algorithm, but still very fast. So all the arithmetic is pretty good. Has a lot of good feature. The other thing that we like, of course, is that there are no known vulnerabilities to quantum computers, in the sense that, of course, these things are not affected by Shor's algorithms. I think the best thing that we can do is apply a Grover search, and this kind of halves the exponent in the security level, yeah, roughly. And of course, the drawback is that we have to publish a very large matrix. So McEliece's original proposal was 500 by 1024. And so it's a lot. It was already like 65 kilobytes. And this is obviously more now for modern levels of security that we desire. So there's definitely a bad feature. So here's what McEliece looks now in a modern fashion. Very simply, we choose error-correcting code. And the private key, I would just say, I'll just store whatever description delta allows me to decode. Yes, so this is more generic way of describing this, because again, this could be, say, the GOPA support and polynomial if I'm using GOPA codes, or the sparse parity check matrix if I'm using LDPC, or whatever other class of codes. Yeah, so generally, I think that my private key is essentially the decoding algorithm, and in fact, one valid choice of scrambling is the systematic form for the generator matrix, so I don't have to do S and P anymore. I can actually just compute the systematic form, and this is enough to hide the structure. And then to encrypt, very simple. I take my message, put it into a code word, and then I add the errors, as I said before, and then the decryption just brings back the code word into the code, and then essentially does the decoding. Yeah, so it's extremely simple description. Okay, so next up, NeedleWriter came up with this proposal, which is kind of considered a dual version, perfectly equivalent in terms of security, and is based more directly on what we call the syndrome decoding problem, which is well known to be NP-complete, and is the following. Given a matrix, H, which ideally is like a parity check matrix for a code, yes, and then a target vector Y, and a weight, find a low weight word E that has that vector Y as syndrome. So, this gives us, first of all, this gives us a unique solution if the weight W, which really should be omega, is below a threshold, which is what we call the GV bound, Gilbert-Rashomov bound. And so we are guaranteed a unique solution. And then this is NP complete. In fact, the hardness, if I'm not wrong, goes even a little bit beyond the GV bound. So you could have like maybe a little bit more than that. But anyway, as long as the weight is very low, relatively low, then this is hard to find. Of course, if the weight is then too high, then it becomes a simple linear algebra problem. Yeah, this is not hard anymore. It's also easy to show that this is equivalent to decoding random linear code. So this is what NeedleWriter is based on. McEliece is based on an equivalent version of this problem where we treat this as I have a code word, find the closest. So I have a noisy code word, find the closest code word to this one. So the two problems are interchangeable very easily. The difference with NeedleWriter's version is that the scheme is deterministic, unlike McEliece, because remember in McEliece we sample an error vector and then we add it. So essentially we are randomizing the encryption process. NeedleWriter does not do that. So the setup is the same, except that we use a parity check matrix instead of generator. And then to encrypt, we don't use a code word. We actually encrypt as a syndrome. So we have to put our message into an error vector. And this traditionally was an annoying thing to do because you have to use these constant weight encoding functions where you take, your input is a bit string, yes, and then you have to like transform it into a constant weight string, which is annoying. But this is not a problem anymore now in a lot of situations where we actually use these things to encrypt, for example, keys for symmetric schemes. Yeah, so if you use this as like a key encapsulation mechanism, for example, this is overcoming this difficulty. And then the decryption is the same. Yeah? Decryption, again, recovers the error vector from the decoding, and then that's actually your plain text. Yeah, so it's pretty much the same as McEliece, except that we use parity check matrix and syndromes, and the scheme is now deterministic. This presents some advantages and some disadvantages. Mostly we like it, again, when we do things like key encapsulation mechanisms, it's easier, it's nicer, it's tighter to get, for example, CCA conversions and things like that. Okay, so this is traditional, and it's been like this for many years, and then people tried other class of codes with very mixed results, mostly bad, because they were just too strong, too good. And then they kind of abandoned that idea and say, okay, now we can try to shrink the key by using compact matrices. And so One idea that I already mentioned is to use quasi-cyclic codes, where all the matrices are formed by circular blocks. Yes, and you can see this is an example where we take cyclic shifts. So each row is a shift of the previous one. And of course, if you do this, you don't need to describe the whole matrix, you just need to describe the first row of each block. But we could do other things. For example, an idea that was in literature by Mieszkowski and Barreto was to use quasi-dyadic codes. Again, we always use this quasi rather than the full, right? So we have blocks, and then each block is like this. So this kind of this recursive structure where we have like an A, B, B, A. This is a dyadic block, and then each of these becomes a C, D, D, C block, and then so on. So it's like a 2 by 2 by 2, power of 2 by power of 2 recursive structure, yes? And but when you look at it in this way, is also just another permutation that you're applying to the first row, essentially. And this is where our work is leading. Yes. So with traditional choice of codes like GOPA or GRS or generalized Vivastava, which I also put in the pot back in 2011, we can find descriptions. Of course, you have to be careful how you choose it, right? So the GOPA code, you have to choose the GOPA polynomial and the support in a certain specific way so that you get your code to be quasi-cyclic or quasi-dyadic. Yes, so you have some constraints. It's possible to do it. But as I was mentioning before, we're putting extra structure in there, right? So you're not just choosing like a random polynomial and a random bunch of elements for your support. You're actually choosing them quite particularly, and so the attacker knows more stuff. And then first attack of the series was this critical attack by Fougère, Otmani-Perret, and Tillich in 2010, which is now just called FOPT. And it was the firstborn of a whole series of attacks based on extra structure that you put in these kind of cryptosystems. And this recovers the public key, the private key, or actually an equivalent private key, but that doesn't matter, very quickly in a matter of milliseconds. So that was devastating for most of the things. And then, we've been working on fixing, and then another attack came out, and then another fix, and then after a few ping pongs, then things start to become a little bit less reliable. And also to do the fix every time you're kind of giving away something, right? So then the keys are getting bigger and bigger, and then ultimately this is not really looking like a very promising research direction. And I think NIST acknowledged this. There were two proposals to the standardization process. One was mine, and another one. So mine based on quasi-dyadic, the other one based on quasi-cyclic algebraic codes. They were not extremely, they were good, but not deemed extremely promising in terms of standardization. And so we definitely agree that this is not what we should keep doing. Yes. So for example, to escape this attack, in the case of quasi-cyclic GOPA codes, you have to take an extremely large base field, something like 2 to the 16 or 2 to the 20, and then of course the keys get bigger and bigger, yeah. Okay, so this is a good idea, but it just doesn't work as well as expected. And okay, so let's do this, but with codes that have less inherent structure. So sparse metric codes is our way of describing, in general, codes that are just characterized by a very sparse parity check matrix, like LDPC. LDPC, again, as I said, they're used in communications traditionally for a variety of reasons, and they have a constant row weight, very low, okay, something like 10 or 20, yes. And so if we choose an LDPC code and say we write H as H0, H1, then we get a parity check, we get a generator matrix by just inverting the leftmost block. I think there should be H0 inverse, but anyway, you get the idea. This is the systematic form for it. And the good thing about this is, as I was saying, this is a perfectly good scrambling method, because the only thing that we need to hide is our private description of the code, which is the sparse one. And if you do this, this inversion here gives you a dense matrix. And so this block here on the right is dense. Yeah? So this is why we don't need to do SGP anymore, because if we do this, then this is a dense block and it's looking completely random. Yeah? So the only thing that we need to protect is this sparse description here, with a lot of zeros and very few ones. There you go. So this is a natural choice of public key for McEliece. And we have this very efficient bit flipping algorithm, which is a little bit different from the traditional algebraic decoders that we use in coding theory. That is all about solving equations and stuff like that. This is probabilistic, is an iterative decoder. We have a bunch of checks that we check, and then you see the ones that are most likely to be verified, and you flip the bits, and then you do it again. Yes, and so this works very well and is very fast, except it has a small failure rate. Of course, at some point it could happen that you make a bad decision, and then things essentially goes out from there, and then what you get is a decoding failure. But this can be, so this is usually about 10 to the minus 7 to 10 to the minus 9, and can be decreased with a variety of techniques, one of which is, for example, the simplest one, to just increase the block length. Yes. Okay, so this is a nuisance, and we'll get back to that. But what else is good about these codes is that distinguishing the public matrix from the private one is really, so you have a public matrix which is dense, and the private one is sparse. So what you're really doing is you're looking for low weight code words in dual. Yes, you're looking for code words that have, again, low weight. And so this is essentially a decoding problem. So the two assumptions that traditionally are separate, one is it's hard to decode. This is kind of what protects your ciphertext. And the other one is it's hard to figure out what the private key is from the public one, and this protects your key. These are two separate things in code-based crypto, and we've seen that we have problems most of the times with the key, actually not with the decoding. Right? So if you assume that the code looks random, it's fine. Decoding is hard. We can really rely on that. So the problem is a lot of the times we think that the code looks random enough, and then as we've seen, that's not the case. And so in this case, the distinguishability part, this is, again, a decoding problem. So we don't have two assumptions. We actually have pretty much the same assumption for it. And in this case, the best attacks, again, we pretty rely on the fact that the decoding is hard if the code looks random. And then we can only do stuff like ISD, information asset decoding, where we're trying more or less, and with many variants over the years, but essentially we're looking for a good set of columns that doesn't carry errors, and then we just recover the code from there. So we're just really kind of trying. So of course you can do better things, as I was saying. You can do some birthday paradox stuff, and you can improve this algorithm, but it's still exponential time. And then of course the idea was that because we rely on these low weight code words, if we increase the weight a little bit, so instead of taking LDPC, actually you have extremely low weight, we take something like a little bit more, and we call this MDPC for moderate, then this should be better, right? So we change the weight from extremely low to something like square root of n, where n is the block length, not the block length, the code length. And then we're still able to apply the decoder from before. So of course you get worse performance, but we don't really care very much about that. We care a lot more about, this makes security stronger. So it looks like a good trade-off. And this paper came out in 2012, and since then, MDPC have enjoyed quite some success in the code-based crypto community. Yes, so the idea is that my matrix is still sparse, but not dramatically sparse. So I'm still able to decode, but it's obviously harder to look for low-weight code words because the weight is higher. Okay, now, of course, we could use LDPC, MDPC plainly, but the code lengths are very, very long, so we're back to square one. So then we should try to shrink the key, and now it's possible to do it. In fact, we have less constraints than before because we don't have to actually make sure that, say, our polynomial and support verify this in this condition. All we need to do is just take a low weight, say, first row, and then we build the whole circle unblocked by just doing the shifts. So we're absolutely free to choose this as we please. Yes? And so this is really what you do. If you want to generate a QC MDPC code, you just choose blocks, you just choose the first row of each block at random, and then you just generate the whole block by shifts. There's no other constraints. Yes? And in fact, this can be described very easily as ideals of this ring, this polynomial ring. So then this gives us a nice polynomial arithmetic. And in fact, the QC property alone does not provide a structural attack, as I was saying before. Still, there's a couple of issues. We have a possible speed up in the information set decoding, what we call the DOOM, or decoding one out of many attack, because each instance of a decoding is really just a shifted. So if you compute the syndrome, each row is just a shifted version of the previous one, and then we have like a whole bunch of samples that correspond to the same problem, essentially. So we get quite a speed up. And also, these allow us to mount reaction attacks. And I'll talk about this in a minute. Okay. So our idea was, okay, now we have QC MDPC, QC LDPC. They work very well. They're not perfect, but can we use something different? And so we came out with this generic framework, which is what we're trying to do. And then once we have a generic framework in place, we can then use it to generate our own sort of method for describing compact matrices. So in general, what we call a reproducible matrix is a matrix that can be described entirely by a set which we call a signature set. This could be, say, the first row or the first 10 rows or any like subset of the rows of a matrix. And then a family of transformations, linear functions that act on this set. Okay? And of course, we can generalize this to quasi-reproducible if we do this block by block. And then if our code is described by a reproducible or quasi-reproducible matrix, then we say that this is a quasi-reproducible or reproducible code. Okay, so this is trying to capture all that was done so far in terms of compact matrices. In particular, as a special case, so in general, we could take these transformations to be anything. Yes, any function that takes a set into the set or a row into another row. Yes. Now, if these are, say, P by P matrices, where P is your block length, and we can assume without loss of generality that one of them is the identity, then we consider the set of all reproducible matrices defined by these transformations, and we get the following properties. That under addition, we have an abelian group, so this is pretty good. So we sum reproducible matrices, and they preserve the same structure. And then the multiplication is distributive. So we get the following result, that under multiplication, we have a semigroup, if and only if the action commutes on the matrices. So we have very strong addition, somewhat weaker multiplication, and the structure that we get is a pseudoring, what we know in mathematics is a pseudoring, and we just call this the reproducible pseudoring induced by F. Okay, so if we take matrices connected to a specific set of transformations, then we have a pseudoring, which means we can combine them together and they're still reproducible. Even further special case, because this is what we've been doing in literature so far, suppose that M is equal 1, so we're just choosing actually like one row, for example, the first row, and then the sigma i's are permutations, then we can describe this in terms of bijections, where we have a 1 exact in position Vz. Yes? So each matrix is a permutation matrix. And then we can get the inverse in this way, and then we can compose them, and we get that the action commutes in this way, essentially, for all ij from 0 to p minus 1. And, for example, there's always this property here, and we can always find an inverse. Yeah, we can find one that composes to the identity. And we get a ring. So if we have permutations, multiplication is actually stronger, and then we get a ring, and then the vertible elements form a multiplicative group. So this is what has been done, for example, for, again, quasi-cyclic codes, yes? But then the situation is even nicer because we can show that the set is closed under transposition too. So if we take the transposed, then this is still reproducible with the same structure again. And, well, then if all of these conditions are verified, then what we can do is consider, say, a block matrix where we have block by block reproducible matrices, and then we call the determinant of A. The determinant of A will be also a block matrix, a matrix. And so if we take the inverse, then the determinant is, so the A inverse is the inverse of the determinant times the adjugate matrix, and these are all reproducible with the same structure, and so what we get is that the inverse of the matrix is also reproducible in the same way. So it's really quite a strong setting, and we think we can generalize all these results to M larger than 1, 2, still with permutations. But what has been done in literature so far is just considering shifts of the first row. Yes, of course, if you have like a larger signature set, then your reduction in key is somewhat less, but this is exactly what we're trying to explore. Okay, so permutation pseudorings is very strong. Here are some known examples of how we can describe things that already exist in our framework. So circular matrices, what we saw before, they give us quasi-cyclic codes. Then the signature is just the first row, and the set of transformations is just powers of pi, where pi is the cyclic shifts. Yeah? So it's described in this way. And then this is the bijection that I was hinting at before, yes? And so you can see that essentially you can compose this many times, and then you get a shift by whatever number of positions you want. And so yeah, we can verify that theorem 2 and theorem 3 are satisfied and everything works. And in fact, multiplication is even commutative. So we have an even stronger, yes, we have an abelian ring. So this was the QC case, which is everywhere. This is what people have been doing always. But even the dyadic matrices we can describe in this framework. As I was saying, dyadic matrices traditionally are easy to generate. You just do this kind of recursive structure, but you can think of them as just a different permutation on the same signature set. Yeah? So you take the first row and you do a permutation in this way. This is the binary XOR on the index, right? And then you get the matrix exactly looking like this. Yes, and again, you can verify that theorem 2 or theorem 3 are satisfied. Multiplication is commutative. This is an even stronger case because the dyadic matrices are symmetric too. Okay, so this is not necessarily an advantage, actually. Okay, so those are two examples. Basically, they are the only two structures that have been explored in literature, and then we just want to see if we can do something different. Yeah, so right now we are setting up a generic framework. Now let's talk a little bit about codes in reproducible form. So we have many possibilities, of course, because as you can imagine, you can choose any number of rows and any sort of transformations that you want. So let's forget about the pseudoring now. Let's just try to get a generator matrix. And this is kind of a central result in our work. If we choose G to be reproducible with a certain signature, n by n, again, this could be one row or more than one, and then this set of transformations, we try to form H so that this is 0. And then we call the subset of the rows in position is plus 1. We take them block by block. Then we define this function f, which acts on indices, right? And verifies this condition. Then we know we have the G and H are orthogonal. And so if G and H are orthogonal and G is a generator matrix, then H is a parity check matrix. Yeah? So then we have exactly a choice of public key and private key for McEliece. Of course, we have to verify that we get full rank, so this could fail, but we then just try again. Yes. So these are natural candidates for generator and parity check matrix, which again we could use for McEliece or in the writer. Yes. So we don't worry over much about the pseudoring, which are actually trying to get directly generator parity check matrix, and the condition to be satisfied is this one. Here's, for example, some constructions that we explored in the paper, and that I think we are going to expand more on. Would be interesting to deploy. One uses householder matrices, which are matrices that are at the same time orthogonal and symmetric, so very specialized. And we can create our parity check and generator in this way. We select V householder matrices, and then we form these binary tuples, which are identical up to order. And then we set up the transformations as just a product of some of them, which are indexed by the first one. And then this H is what is going to form the rows of the parity check matrix. Again, is a product of some of them indexed by the second tuple. Yes? And then once we have H, this is a parity check matrix, so then we can form a generator matrix by just choosing, say, M code words, and then we just build a reproducible generator from that. Yes? So with this, we get a code which has length n and dimension m times 2 to the v, and then the rate is actually close or equal to 1/2, which is most often the desirable choice in code-based cryptography for a variety of reasons. Yeah, so rate 1/2 means that it's dimension to length about 1/2. So this is one example. The other one, in fact, this is something that again boils down to what was done before, is using powers of a single function. For example, with circulant matrices, right? So with circulant matrices, we choose the function to just be the cyclic shift, and then we take all the powers of it. And this is the generalization of it. So we start from a n by n matrix pi, and then, at some point I'm going to get the identity, right? And then we can build a family just as powers of. Yes, and then we get the parity check matrix in this form. Again, if you think pi is a cyclic shift, then we get exactly a circulant matrix. Yes, and then again, we can form the generator matrix by choosing M code words, and then we get a code with these parameters. Okay, so these are just, again, some generic descriptions of things that we can do using our framework. Now, of course, a crucial point is if we're doing this for sparse metric codes, we have to preserve the sparsity. So permutations are a natural choice. So so then we all do this, the signature set that we choose has to be sparse enough. And then the set of transformations has to preserve the sparsity or at least not increase it too much. And then once we have that, it's nice because we've shown before that this is preserved. So if we then choose S, which has the same reproducible structure, and then we multiply it, then we get something that is dense. Yes, and then this is a natural choice for public key. Yes, so again, from theorem 1, we can show that all the entries belong to the reproducible pseudoring, and then we maintain the same reproducible structure. Yeah? So this essentially, if for example was done with quasi-cyclic codes, you choose your transformation to be also, say, the inverse. So in that case, it's very easy, right? Because you have this polynomial ring, and then you have one block, two blocks. These are just two polynomials, and then what you do is you just multiply by the inverse of one of them. Again, that's like a polynomial. So yes, inverse of a polynomial is a polynomial, and then you get another circular block. So this is exactly what you're doing, is you're multiplying by a matrix that has the same reproducible structure, yes. So if family is 1, and then we have permutations like quasi-cyclic codes, then we can have any number of blocks. Again, traditionally this is 2 for QC, LDPC, MDPC. And then we just form the public key by taking the inverse of the first block. If, furthermore, we satisfy theorem 3, we can get a generator matrix from it and use McEliece in this way. So we take just 2 blocks, for example, and then we multiply by S. And then we have H1 transposed, and then minus H0 transposed. And this is essentially what we do in bike 1. So we were already inherently doing bike is one of the 3, or my 3 these proposals is one of the most well-known proposals in the code-based crypto setting.
So can you say something about how efficient the decoding is for that?
For bike or for? Yeah, so if we use the quasi-cyclic codes, it's pretty efficient because we have this description in terms of polynomial arithmetic. So of course this is again something that is a trade-off because if we use like a more generic, something we can play on. So with quasi-cyclic MDPC, LDPC, we get a very efficient decoder. There is a lot of variations of the original decoder from Gallagher, and it's very fast. A little bit harder to do with constant time, but it's something we're working on. But anyway, yeah, so if you do give up the polynomial, then you have to find something that is equally good, for example, and that's one of the points. But it may be worth it, for example, to have like a slower decoder if you think that this is going to give you more security, for example, or defeat some attacks, right? So this is, right now we only have the one option, and we're trying to put more options on the table, yes. So yes, the decoder for bike is actually pretty good. The one for LEDA, which is the other proposal that is based on LDPC, with 2 of the authors that are in this work, it's even better decoder because they actually use LDPC rather than MDPC. So these are very fast decoders. But again, we are interested in preserving the security first of all, right? Okay, so yeah, so what's the point is that we're hoping to defeat attacks, first of all. So one big problem with this class of codes is reaction attacks, yes, which is something that in cryptography is perfectly legitimate. If you just collect, for example, a whole bunch of ciphertexts and decryptions, and then you just see every time the decryption fails, this happens, 1 in a million times, yeah, or something like this. Well, you can collect many signatures, many decryption failures, and then every one of them gives you a little bit of information about the secret, yes? And so eventually, this attack by Guo, Johansson, and Stankowski, they show that they're able to reproduce what we call the distance spectrum of the code, which means exactly like the distances between all the ones in the parity check matrix, yes? And this, of course, is possible. So yes, they recover the set of all the distances in the code. As I was saying, this is possible because in QC codes, we just have every row that is a shift of the previous one. And so all the distances are actually computed cyclically. And then all the rows have the same distance spectrum. So you see that this kind of attack is actually pretty easy, right? It makes sense because you can just do it and the distance is always the same. But this is not true in general for reproducible codes. So for example, if you use something like quasi-dyadic or some other type of structure, then the distance in each row are different, right? I have a 1 here and a 1 here, and then the next row, the 1 is here and here. It's just a permutation. Even just a different permutation will throw this off. And so in fact, we are removing the basis for building this kind of attack, or at least hindering it. So actually may be entirely impossible to set up this kind of attack. Because you're trying to recover the distances in the code, but now every row has a different set, and then it's at least much harder. Yes, so this is one of the reasons why we started looking at other possible structures, is that if you use QC, then again, it's very good, but as it tends to happen in cryptography, something that is very good is also very good for the attacker. And so you have to be careful. You obviously want something that is good for you, but not for the attacker, yes? So it looks like QC is a very simple choice of transformation, but it carries some advantages that carry over to the attacker. The other thing that we hope to improve on is Doom. As I said before, this is a technique to speed up the search on the information set decoding, and it exploits multiple instances of the syndrome decoding problem that have the same solution. Yeah? So basically, from one instance, you can get other instances just by taking shifts. And in fact, this gives a speed up of about square root of n, where n is the number of syndromes that you consider. And in the case of QC, yes, you can get multiple instances just by cyclic shifts of the initial syndrome. This is the problem. And again, this is not the case if we take more generic reproducible codes. So what we're hoping is that if we use a different kind of structure, then we don't get this sort of speed up anymore. And so if you abandon the cyclic permutations, you can essentially force your opponent to consider multiple instances that have higher Hamming weight, about 3 times, and then the advantage is lost. And so, in fact, there is no gain in applying Doom anymore. And so these are two things that we hope to improve on. Of course, we don't want to lose the advantages of having, say, efficient decoders or efficient arithmetic. So the game now is to try to explore the framework, which is defined in general, and see, okay, what is the ideal choice of signature set transformations that still allows me to do things efficiently, but defeat these kind of things. We have a couple of ideas. The first one is to use quasi-dyadics, just because it's already known, and it should be very easy to deploy. In a sense, this is less obvious than circulant, because we're not doing the cyclic thing anymore. And it still allows for efficient arithmetic. So what we found with Paolo Santini, which is my co-author in this work, and then Paolo Barreto and Gustavo Banegas, and this was a paper at MathCrypt last year, if the dyadic matrices it's possible to operate on them entirely using just the signatures. So we can compute the product of dyadic matrices and the sum of dyadic matrices and the composition, everything, just using the signatures. And so that allows for very efficient arithmetic, of course. We even have some improved techniques. We have a dyadic Karatsuba multiplication for multiplying dyadic matrices, and then we have efficient ways of inverting, because, of course, all our codes are quasi-dyadic, but purely dyadic matrices are very easy to invert too. They're just actually self-invertible up to a determinant. So if you multiply A by its transpose, then you get diagonal matrix with the determinant of the diagonal. So that's naturally very easy to invert. Right? So you can exploit this and try to invert the matrix more efficiently. So actually, the arithmetic that we get for dyadic matrices is better than the one that we get for polynomials, because, for example, inverting a polynomial is nasty, right? Whereas inverting dyadic matrices is much better. So this was good. So it's possible to do very efficient dyadic arithmetic. And it's easy to design a cryptosystem, say, a la bike one. And we just choose dyadic blocks here. We multiply by a dyadic transformation on the left, and then we get our dense matrix. Yes? For systematic form, of course, we have to be careful. As I was saying, this in a sense is obvious, but before we have seen that actually dyadic matrices are very powerful. They're very structured. So we can't just use the systematic form, because that would not be dense anymore, right? Because the point is, if I do the inversion on a polynomial, and the polynomial is sparse, so it has like very few coefficients, right? Then the inverse polynomial is very likely dense, but the inverse of the dyadic matrix is still sparse. So we cannot do that anymore. And moreover, the matrices are symmetric and orthogonal. So we have to be a little bit more careful. And instead of using just 2 blocks, we could use 2 by 2 block matrices. Yes, rather than, so we can use like a proper quasi-dyadic matrix rather than a fully dyadic matrix. And then the inversion is still efficient, but then we can lose the sparsity. Okay. Of course, as I said, these are very powerful objects. So we have also to take caution with ring homomorphisms, which have been a problem for the dyadic case when we applied to the algebraic codes. I should know something, because there was a very recent attack about it. So it's possible to exploit the dyadic ring, the ring of dyadic matrices and its properties. So again, you have to take this into consideration when you design the scheme and when you try to look for parameters. But in principle, what we like about this is that the arithmetic is still good, and then we lose the two properties of cyclic matrices or circular matrices that we had before. So if we did that, then we would not have doom and we would not have reaction attacks, essentially. Yes, because we don't have that cyclic distance anymore. The other thing that we thought about is just to generalize the idea of circular matrices to still circulant, but not just the first row. And so it's what we call blockwise circulant. And so we could take m independent rows, and then the functions act on blocks. And so again, it's like powers of a single function, but block by block. So they're like blockwise circulant matrices. And so we have a p by p reproducible matrix. This actually is a nice example too, because it's a proper example of reproducible, which is not just the first row. It's a block. And we get a reproducible pseudoring. And in this way, we lose the property about distances, because now the first m rows that we're choosing in our signature set are independent, so they all have different distances. So we're still circulant, we're kind of blockwise circulant, but the distances are different. And so reaction attacks are at least hindered. And also this is nice, it's a novel construction. This was never appeared in literature before, unlike the dyadic construction, so we thought it was of independent interest anyway. And the sky is the limit in a sense, because these are just some simple, it's just the first thing. Just with these things, set up the generic framework was about 30 pages of paper. So then we said, okay, we'll set up the generic framework, and then we'll expand on that in successive works and see, okay, now let's try to find some constructions that still preserve the efficiency, for example, but give us an advantage on other sides. Yes, so now we have a generic framework. It's just a matter of playing with the signature set and the set of transformations. If you can think of some transformations that are, say, permutations, or some linear transformations that do not enlarge the weight. And of course, right now we've done all of this for sparse matrix codes, but the reproducible description is valid in general for any matrix. And so if your scheme uses random matrices, for example, then it's even easier, right, to devise a reproducible matrix, because we don't even have to worry about the sparsity anymore. So if you look at some of the proposals like HQC, which stands for Hamming quasi-cyclic and uses random quasi-cyclic codes, then it would be even easier to do this because the decoding does not depend on the public code. So it uses random codes, and it would be even easier to do it with a different reproducible structure rather than QC. And it is all. So thank you for your attention. Any questions? Good.
How do you see the attacks evolving in the future? What do you see as the most likely improvements to attacks there?
To attacks on this?
Yeah.
It's hard to say. I think, right now there's a good amount of work that is done on reducing the failure rate to ensure that kind of reaction attacks and things like that are not feasible. I think I don't see many. I mean, the point is that less is more, yes, in this case. So if we only take codes that you have to protect the sparsity, like LDPC, MDPC, then there's really not much that the attacker can look for other than look for low weight words and exploit properties of the matrix. So the less properties we have, the better. Sparsity of the matrix can be exploited with things like Doom using ISD. Other things like reaction attacks take advantage of the decoding failure, but I don't see. Unless you introduce some more dangerous things in the matrix, I don't see any other attacks coming out on this. Of course, you never do until they come out. But yeah.
So the codes that are used in the constructions, they're all linear codes?
They're all linear codes, yes.
So I was wondering if this gives some, for example, like additive homomorphism property to the resulting crypto system.
Yeah, so the main problem for these kind of things is that it's very hard to control. So you have additive homomorphism property, but then the weight of the error vector increases. Yes, every time you sum to ciphertext. So you could do this maybe once. But already if you're like way below the threshold, then there's some problem, and then maybe if you add to ciphertext, you're right at the GB bound, and then you cannot do this more than once.
Oh, okay.
So the problem with, you cannot do it straightforwardly, not even for addition, because the problem is that you're using sparse. And this is not as good as lattices, where you have, your definition of metric is different. So in lattices, you have a lot of little positions everywhere, and so you can sum them together. But here, this relies on, it's binary, first of all, and it relies on having a lot of zeros and very few ones. And so if you keep summing sparse vectors after very few times, you already go beyond the threshold, and this is not secure anymore. So linear codes are good, yes. If some code word, you can add the code word, but the error part is the problem, and this is not immediate how you do this. Yes.
So I guess, another question following that is that has people looked at nonlinear codes?
Not that I know of nonlinear codes. I think it would be awkward to describe a scheme with nonlinear codes. I don't know exactly what happens also in terms of decoder. But there is one construction that I think I was mentioning to you that uses, that tries to do homomorphic encryption, but in a different way. So it's not exactly McEliece or the writer scheme. And they kind of control the error vector in a different way. Yes. But it does not involve nonlinear codes.
Well, thank you.
Good. Thank you.